common evolutionary theories that everyone gets taught. So if you're serious about it, good to have things in the back of your head, go down some rabbit holes, and roll some videos.
Steve, thanks for letting us stop at the river on the way to Norway. It's a beautiful place. This is where the conventional story tells us it's this river that carved all of this out.
It is. And as we look at rivers, there's a power in thinking about a modern river and what it might do, such as erode a big canyon. Let me show you two things right away, and let's delve into some thinking about the canyon. We have a 10,000 cubic feet per second flow down the Colorado River here, presently, and we have this granite gorge sitting here. Do you think that granite gorge was cut by the action of a flow like this?
That's what the story says.
That's what the story says. There are historic photographs about 150 years old showing rapids here in the Colorado River. And we can come back and look at the rapids now. The boulders in the rapids haven't changed position. It's interesting that the rapids haven't changed over 150 years.
So there have been some pretty big floods between then and now.
Yes, there have been floods over 25 times the present flow of the river. 250,000 cubic feet per second have been going down the channel of the Colorado River. That's a really big flood. Okay, but it still didn't move the boulders. Okay, and the channel is lined, the side of the channel of the river is lined by slope boulders that have fallen into the bank of the river, and the bank of the river is stable, not just the rapids. And the bottom of the river is stable. It's full of gravel and sand. So the Colorado River isn't deepening or widening the canyon. So the ultimate question is, what cut the Granite Gorge?
Right, if it wasn't the river, then how will we get all this material out of here? Well, Steve, thanks for letting us stop at the river on the way to Norway. It's a beautiful place. This is where the conventional story tells us it's this river that carved all of this out.
It is. And as we look at rivers, there's a power in thinking about a modern river and what it might do, such as erode a big canyon. Let me show you two things right away, and let's delve into some thinking about the canyon. We have a 10,000 cubic feet per second flow down the Colorado River here.
I had no idea how many crystal shops were in Sedona.
No, and I'm glad to let you stop by because I wanted to get this piece of petrified wood. Arizona is famous for its petrified wood, and it's part of what we need to discuss here.
Well, when we were talking about isotopes, one of the things we didn't address was the whole area of carbon-14. I mean, most people are familiar, and yet I'm not sure we know exactly what that is. Can you describe that?
Well, first of all, we need to clear up a confusion. Most people think that radiocarbon has been used to date rocks. Whenever they think of radioactive dating, they think of radiocarbon because that's what they're used to hearing. But radiocarbon isn't used to date rocks because most rocks don't have carbon in them. And what we need is organic carbon because it's intrinsic to the methodology or how you understand how radiocarbon works.
How does a tree then get carbon-14 in it?
Well, it's simple because the radiocarbon is produced in the upper atmosphere. Cosmic rays bombarding the Earth's atmosphere turns nitrogen atoms into carbon-14 atoms, which circulates into the carbon dioxide that we breathe. And so it's also taken in by the plants during photosynthesis. So it's in the wood, it's in the leaves, it's in the vegetables we eat. Animals take it into their bodies, so it's in the animals that we eat. So it gets into our bodies. So not only are all of these plants around us radioactive with radiocarbon, but we are ourselves.
So you have it, I have it.
Correct. And as long as we live, we're taking more radiocarbon into our bodies. But when we die, we stop taking radiocarbon into our bodies. And so a dinosaur dies, it stops taking in radiocarbon, and then over the thousands of years, it's getting less and less radiocarbon. As I said before, after 90,000 years, there should be no radiocarbon left in dinosaur bones. if every atom of the Earth was radiocarbon, it all would have decayed away in less than 1 million years. So if you already believe the fossils, dinosaur fossils, the coal beds, all those things are millions of years old, you wouldn't expect to find any radiocarbon in them. And yet you do. And this is one of the things that we found when we studied petrified wood like this at different levels in the geologic record. I was doing research on this. I was collecting samples in England, in Australia, and I sent them to radiocarbon laboratories, and sure enough, they had radiocarbon in them. So this is another aspect of this whole time question, because if these things are believed to be millions of years old, like this petrified wood, and yet it has radiocarbon in it that says it's only thousands of years old, then it means that it calls into question the conventional time frame. And so we wanted to test this because we'd seen in the literature, this is in the conventional literature, in the 1980s they developed a new methodology for measuring radiocarbon. They could count atoms of radiocarbon. That's how good it was. But they wanted to be sure that they weren't getting any contamination in their laboratories. And so they took samples like petrified wood, they took samples of dinosaur bones and coal and oil and natural gas and limestone even, and they put them in their equipment, and every sample they tested had radiocarbon in it. And this was reported in the literature, and they ignored it. So in our research, we decided we'll test that for ourselves. We wanted to be sure that this wasn't an artifact of the conventional experimental method. So we selected samples from 10 different coal beds around the United States. Some coal beds that were conventionally as young as 40 million years, some coal beds that were conventionally over 300 million years old. And when we tested them for radiocarbon, they had radiocarbon in them, and they all yielded the same radiocarbon age, which meant that these plants must have all lived at the same time and died at the same time. And that fits the flood paradigm, because these would have been pre-flood trees that were all buried together at the same time. But we went further.
I had no idea how many crystal shops were in Sedona.
No, and I'm glad you let me stop by, because I wanted to get...
We're at this incredible computer history museum with all of the artifacts that show us the progression of this amazing technological revolution that's occurred.
Right.
And no one would question it.
Yeah,
I mean, we have the artifacts, we have the history, the historical statements, but when we move back
We have to
to
see
origins,
Right.
and this is your expertise,
I know.
we have artifacts and we have historical documents, but all of a sudden we have radically different opinions of what those artifacts and that history says.
Radically different. In fact, you're looking really at what are competing paradigms. A term that I first encountered as a 19-year-old art school dropout reading Thomas Kuhn's classic, The Structure of Scientific Revolutions, which revolutionized my own understanding of science. And you gain a vision from that book of science as a creative human enterprise where assumptions can't be escaped. And depending on the assumptions that you choose, you can end up with very different narratives. So we've got data, we've got evidence, we've got, in effect, artifacts, but those pieces of evidence are being interpreted in very different ways depending on the assumptions that one makes. So really, science isn't just about the evidence, it's about how you interpret that evidence. So these competing paradigms will put you in very different places depending on which one you're in.
So it comes down to paradigms.
Oh yeah. A paradigm governs really everything that you think about a particular subject. It provides this global framework. So this room, for example, we've got so-called mini computers here, but really they're not mini at all in terms of our current paradigm.
Yeah, today, right?
Yeah, this.
Yeah.
Right? So really, to understand this question of origins, you really need to begin by looking at the governing paradigms, the two major views that we currently have about the history of life and the history of the universe.
And what are those?
On the one hand, we have the conventional paradigm.
This is the view that the universe began a long time ago in a very simple state, and by strictly physical processes developed gradually and continuously into all the complexity that we see today. Galaxies, stars, planets, cells, animals, human beings. It's one long continuous story from a very simple beginning to today. That's one view. The second view we can call, let's say, the historical Genesis paradigm. Strikingly different. First of all, you've got recency, right? This is not happening over a very long time. It's happening relatively recently, and it begins in a state of functionality where it's working already. You've got organisms present, they're doing what they need to do. You've got planets and solar systems already operating, brought into existence, really within a very short span of time, simultaneously. Homo sapiens is present right there, right at the start. So those two views contrast really at every point, and their key features are also very different.
It's not hard to see there's a radical difference between those two in terms of time.
Right.
What else do you see is contrasted here between these two paradigms?
To me, the most striking difference is what kinds of causes are operating. So in the conventional paradigm, it's physics running the show. Physics through chemistry, influencing biochemistry and then biology. All the change that's happening is coming bottom up from fundamental, undirected, mindless physical processes. They're doing everything. In the historical Genesis view, underlying everything is mind, is intellect. A purposeful intelligence is bringing things into existence. That's a profound difference. Another key difference is the actual sequence of events. So in the conventional paradigm, you have a gradual process whereby things are constructed beginning on what came before. So ultimately, really you start with elementary particles, hydrogen and helium, heavier elements, galaxies are formed, planets, and so forth, leading eventually to the first cell. It's a continual process of gradual transformation. With the historical Genesis paradigm, you have a transcendent intelligence, God acting in space and time to bring things into existence, in a sense, discontinuously. And that pattern gives you discrete events in space and time that aren't strictly flowing one from the other. So you have the creation, you have the fall, which is a catastrophic event that affects all of the creation in a radical way. So again, you see a striking difference in the narrative that one would tell depending on your starting point. And lastly, maybe this is the most important, what is the whole of reality? Is it strictly physical? Are we, meat machines that will decay into nothing upon our death? Or is there a spiritual dimension to our existence that is eternal, that has eternal value? And really, that final point is the one I think that's most decisive because it ends up affecting how we treat each other. And science is one thing, but our moral sense, our relationship with God, we can't have a relationship with God if we are strictly physical creatures.
I guess the computer museum must be a common place.
I think what they do is they have like that setting, and there's a bunch of clips that go to it.
Okay.
I think so.
So that was different, but it was
Good.
the same scene. It was the same setting.
Yeah, they probably do what they
I
can.
like that computing paradigm. I found that useful.
Me too. And this one I thought was fun.
There's also a question that's often brought up about the formation of ice in Greenland, for example, and how that accumulated. There was a recent incident that occurred at the end of the Second World War, which is quite fascinating. There was a squadron of P-38s and a couple of B-17s that were flying from North America over to England at the end of the war. And that was over 50 years ago now. And they got stranded out in the middle of the North Atlantic, so they ended up crash landing on the southern coast of Greenland. But they were rescued about a week later. But the planes were left behind. And there was a wealthy Texan who decided to go looking for these planes because they were very valuable to restore, particularly the P-38s. So they went looking for the planes on the southern coast of Greenland, and they couldn't find them for about a year because they had moved. The ice was slowly drifting toward the Atlantic and carrying off and disappearing. But they looked about 10 miles from where they knew they had crash landed and found them 250 feet down in the ice. What had happened was the average precipitation that occurred on the southern coast of Greenland was an average of about 5 feet of ice per year, solid ice, that accumulated. So in 50 years, you got about 250 feet of ice above the airplane, so they were buried down there. Now, what's that got to do with the Ice Age? The importance of this was, how do you get that kind of accumulation of ice in Greenland in that short of time? The normal amount of ice that accumulates in Greenland is less than a foot a year, typically in Greenland. But on the southern coast of Greenland, where those planes happened to have landed, was where the Gulf Stream intersects with Greenland, which is a warm ocean current that comes up the east coast of North America, and is a large source of water vapor off the coast of this cold continent, very much like what we talked about globally. So this is a small scale event that would produce an increase, 5-fold increase in the amount of precipitation in just that southern part of Greenland and accumulate that amount of ice.
And also the unique conditions you were saying were required.
It was global. It was global instead of just this little local area. So it's very, very convincing. We have been talking earlier about the concept of irreducible complexity when it comes to biological systems. Would it be fair to apply that same kind of a term to what we're seeing here?
Well, it's a really tricky thing because living systems are a bit different from what we have here. I've been wrestling with this idea of design in astronomy for a long time. I think some creationists, some biblical people maybe see design where there isn't any sometimes, but I do see design here. I find it incomprehensible to me that this is all just an accident. Like the moon, the more I study it, the more I'm impressed with what we see there.
Well, what do you see?
Okay, the moon's different. we have like 170 satellites, or natural satellites, orbiting the planets. Jupiter and Saturn have scores of satellites orbiting them. We only have one. Most of the satellites are small. Jupiter has 4 large ones, Saturn has 5 or 6 fairly good sized ones, and the Earth has a good sized one too, even though there's several larger than it is. But the moon's orbit is different. A little tricky. I'll try to explain this best I can here. The sun is 400 times larger than the moon. So if you had a ball the size of an inch across, the moon and the sun would be 400 inches across. Gives you that scale.
That's not what we see, though.
No. Because you see that the sun is not only 400 times larger than the moon, but it's also 400 times farther away. So if you take something and move it as far away as it is larger than the other, they have the same size to us. Both the sun and the moon appear to be about a ½ degree across in our sky. Now, on rare occasions, the moon passes between us and the sun. It doesn't happen very often. About every year and a half, somewhere in the world, usually in Timbuktu. And when that happens, the moon just barely covers the sun up. If the moon were a little smaller or a little farther away, it wouldn't do it at all. If it were larger or closer to us, it would be grossly over total. It wouldn't be nearly as spectacular. We get these rare and very spectacular eclipses.
Do you think that's a design that...
Well, it's either, if you look at the other satellites, 170 or so in the solar system, none of them have those kind of requirements. Either they don't happen at all, or they're grossly over total, so they're not very rare and they're not very spectacular. It takes, I read once that in a given place on the Earth, we get a total solar eclipse about once every 400 years. So either, if you see one, you're either very lucky or you plan to be there to see the thing. And so these eclipses are spectacular and rare, and this is the only planet on which it matters. And it's the only planet on which it happens. I don't find that to be just a coincidence. I think there's more to it than that. But there's another more important thing about it. The moon's orbit is different. We have the plane, the Earth's orbit around the sun. We call this the ecliptic. Imagine a flat plane here. The sun's here at every
every year the Earth goes around like this, and it causes the sun to seem to move through the stars, and that defines this ecliptic across the sky, this big line across the sky, the plane of our orbit. Now, the moon's orbit is very close to that plane. It's tilted a few degrees, but basically the moon orbits around the Earth in the same plane that the Earth orbits around the sun. Of the 170 or so satellites in the solar system, it's the only one that does that. All the others have different orbits. The most common type of orbit is above the equator of what we call the equatorial plane of the planet. And each of the planets have different tilts. Our own Earth's tilt is about 23.5 degrees. So if this is the plane of the Earth's orbit, there's another plane, the equatorial plane, that's tilted 23.5 degrees to that. And if the moon were like other satellites in the solar system, it would be orbiting this plane, not in that plane. But the interesting thing is, that tells me something right away, that the origin of the moon must be different from other satellites. It must be unique, which we kind of know that from Genesis because of the purposes involved. I believe the moon is unique, and the origin scenario perhaps would be unique as well. And, you know, astronomers have tried to claim, well, we need to study the satellites of the other planets, hopefully to learn more where the moon came from. Well, I say nonsense, because the moon's orbit is unique in the solar system. But there's something else about the moon. If you compare the ratio between the mass of the moon and the mass of the Earth, it's pretty high. Earth has about 81 times more mass than the moon does. But when you look at other planets, they have thousands or tens of thousands of times more mass than their satellites have. So when you look at the ratio between the mass of the planet and the mass of the satellite, it's closest for the Earth by quite a bit, Earth-Moon, than it is for any other in the solar system. Now this is tricky. The Earth, you know, has a tilt of 23.5 degrees. That causes our seasons. But perturbing effects, the other things in the solar system are yanking on that tilt. And over time, it would cause that tilt to change tremendously. It would go from being 23.5 degrees to being 0, to being 90, back to 0, and waffle all over the place. It would slowly happen, but it would happen and waffle everywhere. What that would mean is that eventually there would be no seasons. And eventually, most of the Earth's surface would be simultaneously in the tropics and in the Arctic regions. Could you imagine the devastating effect that would have on living creatures? Sure. That's if there's nothing else going on. The planets and the sun and everything else out there would do that to the Earth's tilt.
So why doesn't it?
Because of a very complex interaction of the moon, it stabilizes it and keeps the tilt within about a 2 degree range. It can't leave more than about 2 degrees, which we can withstand that small change. And it only happens, two things are true. If the mass ratio is high, which is unique to the Earth-Moon system, and this is critical, that the moon orbits in the ecliptic plane, not the equatorial plane. And it's the only satellite in the solar system for which that's the case. Now, again, you can argue it's a coincidence. But how many coincidences are you allowed before you're going to realize, well, maybe these coincidences aren't coincidences at all?
So we have this large extent of layers. We have the lack of erosion between the layers. We have the lack of critters turning this thing over. What other evidence do you see?
Well, if we look closely, for example, at the Coconino Sandstone, we see within the horizontal layer, we see the bedding, that there's bands within it that are sloping. We call those crossbeams. And what they indicate is that you have underwater sand grains with moving along. The comparison is in a desert. Most people understand the desert with a sand dune and the wind blowing the sand forward. Well, underwater, we see the same thing, sand waves. And so water current is rapidly moving it along, and what we get left behind are these front-facing slopes. And we can estimate the depth of water, the speed of the water current, and we can do this with the Coconino Sandstone. In actual fact, it's important to recognise that there's a difference in the angle in a desert dune. It's usually 30 to 34 degrees of these sloping beds. Whereas underwater, it's usually 25 degrees or less. In the Coconino Sandstone, these cross beds are always 15 to 25 degrees. So it was underwater deposition.
Well, Andrew, the Coconino Sandstone is a big issue because the conventional paradigm has for years said that this was formed in dry conditions.
Yes, it's given us the textbook example, and it's held to tenaciously, that the Coconino sandstone formed in a dry desert sand situation. You know, those cross beds, everyone agrees that they formed as a result of dunes, but whether it was in air or water is the question. Now, we've examined this issue extensively. Steve Austin's student, Dr. John Whitmore, has combed the hills around here with his students, hundreds and hundreds of measurements of these cross beds, and they all come in the range of 15 to 25 degrees, which is right where it should be with an underwater sand deposition. Added to that, in the Sedona area, we find these strange folded units called parabolic recumbent folds. This is where the water current was so swift that it turned over the edge of the top of the dune.
Kind of like you say, a wave when a wave curls?
Yes, when a wave curls and crashes. And we don't see that in a desert sand dune situation. John Whitmore and his students have examined hundreds of thin sections, looking at the grains, looking at the minerals, and all of those features indicate underwater deposition. You'll be familiar too, in the Grand Canyon, there's evidence of little critters that
Yes,
walk
I've seen those.
on some of those cross beds, and they're always going uphill, up the front face. It's as if the critter is getting buried by the water, it's trying to go up. You can see the sky up there above the water, and it's trying to get up there. Interestingly, many of these, the claws are at a slight angle to the direction that they're trying to go, means they're bracing themselves in the water current. In some places they've been knocked off their feet, and left, right, and it stops, and then you see it again some distance away. They've been moved across. The other thing, you think about these nice, neat footprints. How would you form them in a dry desert sand? There's no cohesion between the sand grains. The conventional paradigm said, oh, well, maybe there was the dew in the morning that held enough water. But that dries out very quickly. And then you get more sand, dry sand, and it tends to distort. These are sharp outlined, and it's exactly what you find in wet sand. And so all of these details together cry out wet sand deposition, underwater deposition for the Coconino sandstone. And the speed, as I said before, if you look at these cross beds, you can figure out the depth of the water current, the speed of the water current, the direction of the water current, and we're looking at the Coconino sandstone, average thickness of about 300 feet over an area of up to 200,000 square miles. That's 20,000 cubic miles of sand. At the rate the water was flowing, you would have deposited all that in a matter of days. Not millions of years, just a matter of days.
Right. So, yeah, just interesting things to think about. So we'll close the break and then we'll move on to the rest of the service. We're so grateful for this time we've had together where we can learn more about your wonderful design for us and for life here on Earth. And as we go into the rest of the service, we pray that you would be with us, that we might just praise and worship